Finally, I want to talk about these formulas for other types of integrals. Integrals like line integrals, flux integrals, and the change of variables formula. So we had integrals involving vector fields, and we had a lot of different theorems saying that, hey, if we do some integral on the inside of a region, that's the same thing as doing some other type of integral on the boundary of a region. But just like with the geometric integrals, the formulas for all of these look weird and disconnected from each other. They involve cross products and dot products and taking all kinds of different procedures. They involve gradient and curl and divergence. And none of these seem to be unified, even though they seem to all have an underlying common pattern of some type. And seeing these in the form that we do it in this class, again, it's the most calculationally helpful, but it doesn't really give us something conceptually helpful. One way to think about this is that when we were doing line integrals, we had this method for doing line integrals using this type of formula where we could just substitute in. We could say, let's write down x as a function of time. Let's write down y as a function of time and just calculate d of those. Dx is the derivative of x with respect to time, and dy is the derivative of y with respect to time. And we plug that back into the integral and just do the integral. We never said you could do this with bigger integrals because you can't. It doesn't work there, but let's talk about what goes wrong. If we tried it, let's try taking dx dy and substituting in x is some function of new variables u and v, and y is some other function of new variables u and v. And then we could calculate what's dx and what's dy. The chain rule says that those are the derivatives of x with respect to u times du plus the derivative of x with respect to v times dv, and similarly for dy. If we followed that formula like this, we'd get that dx dy goes to this big formula here, just expanding everything out. And this is nonsense. So for one thing, we've got du and dv dv here. Those don't make any sense on the face of it because we can't integrate with respect to u twice. Once we integrate with respect to u, the variable u is gone, and we're supposed to be integrating with respect to the other variable. And when we do the actual change of variables formula, we use the determinant of the Jacobian. And if you work that out, it looks like this. This part looks okay, where we've got these two partial derivatives. This part looks okay, except for it's got a sign error. There should be a negative, and there's not. There's a positive. But we can fix that by imposing new rules for this type of change of variables formula. So when we do this, we are led to something called differential forms. We change our rules by saying, instead of writing dx dy or du dv, we introduce a wedge symbol in between them as kind of a reminder that we're doing something different. And we impose new rules for manipulating them. If we switch the order of two of them, we get an extra negative sign. And if two of them are the same, they cancel each other off and we get 0. So for example, if we use this substitution rule, we get a formula for how to integrate a vector field over a surface. We calculate a double integral of p dy dz plus q dz dx plus r dx dy. That's a formula that legitimately gives us the right formula for a surface integral of the vector field p, q, and r. And we still have the formulas for line integrals, and we still can calculate triple integrals of some function f dx, dy, dz. So this is a legitimate means and a legitimate way of thinking about these types of integration. And this d operator that we started to use unifies things. It unifies gradient, scalar curl, and divergence. And the way we apply it is we apply d to the front end part in front and wedge it with what's left over. So d of a function of two variables, for example, is basically just its gradient. It's the x derivative times dx plus the y derivative times dy. It's more general than that, though, because we could use it on p dx plus q dy. If we expand that whole thing out, here's d of p and here's d of q. We wedge that with dx and we wedge that with dy. Expand everything out. The parts involving dx, dx, and dy, dy go away, and to convert dy dx back into dx dy, we have to introduce an extra negative sign out front. And what we're left with is, lo and behold, the formula for the scalar curl. More generally, if we did d of like a line integral, something where we're going to do a line integral of p dx plus q dy plus r dz, we would legitimately get a formula for the actual curl of that vector field in terms of something we would integrate over a surface. So the big unifying theorem then is something called Stokes's theorem. That's different from Stokes's theorem in 2D in that it applies everywhere. And it says the integral of one of these differential forms over the boundary of a region is always equal to the integral of d of it over the inside of the region. It works for the fundamental theorem of calculus with an interval in its boundary. It works for Green's theorem and Stokes' theorem, where we've got a two-dimensional region in its boundary. It works for the divergence theorem, where we've got a three-dimensional region in its boundary, and all of it tracked with appropriate orientations. And so this kind of gives us a unifying version of things, and it continues to work no matter how many variables we have. If we don't have just x, y, and z, but we have an extra time variable, things that are time dependent, this still is a legitimate method and a legitimate tool for attacking those types of problems. All right, thank you.